So in a previous lesson, we've covered what intramolecular bonds are. And what they are the chemical bonds that hold atoms together within a molecule. The three major types of intermolecular bonds that we have covered are ionic. So these are for ionic compounds, and they consist of a metal and a nonmetal. The next is covalent, which belongs to molecular compounds, and covalent bonds consist of two nonmetals. And then the last one is metallic. So the main two that you need to know are ionic and covalent, and you just need to be aware that metallic intramolecular bonds do exist. So for example, we're given water. Now I'm gonna change this Lewis dot diagram into a structural diagram to show it like so. So these bonds right here, those are the intramolecular bonds because they're what holds all the atoms together. And specifically, they are covalent bonds. Now, if you wanted to get even more specific, you could call them polar covalent bonds, just because oxygen and hydrogen have different electronegativities. So that's why you'd be able to call these bonds between hydrogen and oxygen polar covalent bonds. Okay, but moving on to intermolecular bonds. Now, those are going to be the forces that are between molecules. So you do need to know the difference between intramolecular bonds and intermolecular bonds. Okay, so if we're thinking about inter and just knowing or remembering that that word means in between two different things, you could think of it like international trade. So that is the trade that happens between two or more different nations. Okay, so intermolecular forces are responsible for the physical behavior of molecular substances and physical properties such as melting point, boiling point, and the solubility of substances. Okay, so for example, many molecules of water, they stick together in order to form a water droplet. So what's happening here? So these are the intramolecular bonds. Whereas these dotted lines are the intermolecular bonds. And specifically, it's going to be hydrogen bonding, but we'll cover the three different types in a second here. Okay, so main idea here is intramolecular bonds are within a compound or molecule, whereas intermolecular bonds happen between two different molecules. Now, as I said, there are three main types of intermolecular forces. So these are going to be important, and you do need to know these. So the first one being London dispersion forces, or sometimes just called London forces. The second one is dipole-dipole forces. And then last but not least, we have hydrogen bonding. Okay, so what you'll need to be able to do is you'll need to be able to look at a compound and determine what intermolecular forces it has. So let's get into each of these. So London forces, what exactly are they? So London forces, it's just the attraction between a positive nucleus to the negative electrons of a neighboring molecule. So keep in mind that nuclei are positive just because that's where the protons are housed, and protons have positive charges to them. Okay, so if we were to draw a picture of what London forces look like, first of all, I'll start off with my nuclei. So we're talking about two different molecules here. So we have a certain amount of protons, certain amount of neutrons in both of these. And I'm not specifying the amount because this isn't element specific. This applies to everything. Okay, so we have the electrons from this atom, okay, or molecule, I should say. And you know what? I'm going to color code this so that it's easy to see what I'm meaning here. There we go. So we have electrons from this atom or molecule and the other one. So just arbitrarily, I'll call this molecule A and this one molecule B. Okay. So this is just the attraction between the protons of one molecule with the electrons of a different molecule. Or sometimes it's just happening between atoms as well. All right, so what kind of compounds have them? Everything. Why? Because everything has protons, everything has electrons. So all compounds have protons, all compounds have electrons that make them up. Now, the larger the compound, that means there's going to be more protons and more electrons. Therefore, the more London dispersion forces it's going to have. Moving on to the second intermolecular bond or intermolecular force, we have dipole-dipole forces. So what exactly is it? Essentially, it's the attraction between the positive end of one molecule to the negative end of a different molecule. Okay, so how do we get positive and negative ends to molecules? Well, that all has to do with electronegativity differences. So if we're drawing a picture of what this could look like, let's say we take HBr. Okay. So with this, because bromine has an electronegativity of 3 and hydrogen has an electronegativity of 2.2, then there's going to be a dipole moment. Okay, so let's write the electronegativities just above them. Okay, so the side that looks like it kind of has a plus sign on it, that's the side of this molecule that has a slightly positive charge. And the arrow for dipole arrows always points towards the side of the molecule that has a slightly negative charge. So let's write that out. And the reason why I'm saying it's slightly positive, slightly negative, is because the electrons in this bond are still being shared between hydrogen and bromine, just because it is a covalent bond, and electrons are shared in covalent bonds. But because of the difference in electronegativities, it's a polar covalent bond, which means that the electrons in this bond are slightly more skewed towards the bromine side of the compound. So let's draw a few more of these molecules just to demonstrate what we're trying to show here. So the attraction or the dipole-dipole force is going to happen between the negative side that has the bromine on it and the slightly positive side that has the hydrogen on it. So what it kind of ends up looking like, if I were to draw a picture of these with the slightly positive and negative sides, would be like that. Okay, so what kinds of compounds have dipole-dipole forces? That's only going to include polar compounds. Okay, so with London forces, any compounds have London forces. However, for dipole-dipole forces, only polar compounds are going to have dipole-dipole forces. And the greater the difference in electronegativity, the stronger the dipole. Last but not least, we have hydrogen bonding. Now, what exactly is hydrogen bonding? That's going to be the attraction between a hydrogen to a lone pair of electrons on a highly electronegative atom. Now, it can't just be any highly electronegative atom. It has to be either fluorine, nitrogen, or oxygen. So the attraction of a hydrogen nucleus to a lone pair of electrons on a highly electronegative atom. So this has to be either fluorine, nitrogen, or oxygen. So if we were drawing a picture of this, okay, so I'm just going to quickly draw a water molecule here. And we'll draw another one over here. So like I said, the attraction is happening between hydrogen and a lone pair of electrons on either nitrogen, oxygen, or fluorine. Now, hydrogen bonding happens in more specific compounds compared to the other two. So the types of compounds that can hydrogen bond, they must be polar. And they must have hydrogen directly attached to either fluorine, nitrogen, or oxygen. Okay, so a lot of times students make the mistake of, oh, there's a hydrogen as well as one of these in the same compound. That must mean that there must be hydrogen bonding. Not necessarily. Okay, so you do, in order to figure out if a compound can do hydrogen bonding, you will need to draw out what the compound looks like so that you can tell if hydrogen is directly attached to nitrogen, oxygen, or fluorine. Okay? Because sometimes compounds do have hydrogen along with one of these in it, but they're not directly attached to one another. And therefore, that compound wouldn't be able to hydrogen bond. Okay, so for example, does CH3F have hydrogen bonding? Show your work. So let's just first start with the Lewis dot diagram, which is also known as an electron dot diagram, and move on to the structural diagram. So carbon, it's in group 14, so it has 4 valence electrons, and I'm going to strategically place the hydrogens and fluorines, or I guess there's only one fluorine here, but so my bonding electrons are all paired up. Whatever you do when you're drawing your Lewis dot diagrams, never leave a bonding electron by itself. They always pair up. If you have a bonding electron that's not paired up in your Lewis dot diagram, you've done something wrong. So let's move on to the structural diagram. And just for fun, I'm also going to draw this in the Vesper diagram. So because our central atom, which is carbon, has 4 atoms attached to it, but no lone pairs, it's going to be a tetrahedral shape. So I'm going to put my flat bond there, let's say another flat bond there, my wedge, and then my dash. Okay, and notice how these 3, they all kind of point down, whereas this one points up. That's another key point about the tetrahedral shape. Now, this is kind of above and beyond what the question is asking, but it's good review. Okay. So the whole point of this question is, even though we have hydrogen and fluorine in this compound, because none of the hydrogens are directly bonded to this fluorine, that means it can't have any hydrogen bonding going on. So I'm going to abbreviate hydrogen bonding to just H bonding. So no hydrogen bonding because hydrogen is not directly attached to, in this case, fluorine. Okay. But if we were trying to analyze what intermolecular forces this compound does have, well, it has London dispersion forces because everything has, or every compound has London dispersion forces. Okay, and because this is an asymmetrical compound, it's also going to be polar. Okay, if you wanted to draw the resultant vector for this, I'll draw the dipole moments just briefly here, and then I'll draw the resultant vector. So carbon has a higher electronegativity than hydrogen, but fluorine has a higher electronegativity than carbon. Okay, so because these dipoles cancel out because they're in equal and opposite directions, what I can say for the resultant vector is that it's towards the right or towards the side that has fluorine on it. Okay. So I'm just going to write intermolecular forces present. London dispersion forces, so LDF stands for London dispersion forces. And dipole-dipole forces. Okay. So I highly recommend always drawing out the compound just to check to see if it has hydrogen bonding. Okay, just because it has hydrogen and either nitrogen, oxygen, or fluorine doesn't necessarily mean that it can hydrogen bond. So let's actually highlight that because that's pretty important. All right. So intermolecular forces, they can help to determine boiling point. So the boiling point of a compound is the temperature at which it turns from a liquid into a gas. When this happens, you end up breaking all intermolecular attractions. So the higher the boiling point, the more intermolecular forces you're going to have, or the stronger the intermolecular forces that you're going to have. So let's take a look at these four compounds here. So which would have the highest boiling point? So for this example here, the first thing I'm going to do is let's just check for what types of intermolecular forces they have. Okay, so looking at all of these, it's just carbon with one other element in it. And from a lesson or two back, we said that carbon with only one other element in it, in a compound, that's going to be nonpolar. So all of these compounds are nonpolar, which means that none of them have dipole-dipole forces and none of them can do hydrogen bonding because none of them are polar. So then we're just going to look at London forces. Now, since London forces is the attraction between the positive nucleus of one compound and the negative electrons on another compound, we're going to want to figure out, okay, how many protons does each of these have? Okay, so if I look at methane, the first one, then take a look at my periodic table. So carbon, in order to figure out how many protons it has, I'm going to look at the atomic number. Okay, so we're going to count up how many protons each compound has, and then whichever compound has the highest amount of protons is going to have a higher boiling point. So carbon has 6 protons, and then hydrogen has 1 proton. Okay, so 6 from the carbon plus 4, because each of the hydrogens has 1, and there's 4 of them, so this has 10 protons. Okay, same deal here. So carbon, there's 2 of them, so 12 plus 6, that's going to give us 18 protons. With this next one here, we got 18 plus 8, because 6 protons from each carbon times by 3 is going to give us 18. So 18 plus 8, that's going to give us 26 protons. And then for the last one here, so we have 4 carbons, so 6 times 4, 24, plus 10 protons from the 10 hydrogens. That's going to give us 34 protons. Okay, so looking at all of these here, they're already arranged from lowest amount of protons to highest amount of protons. So what I can say here is, because methane, the first one here, has a lower amount of protons, okay, we can assume that it has less London forces going. So because it has less London forces, that means it has a lower amount of intermolecular forces, and therefore, the lower the amount of intermolecular forces, the lower the boiling point. So less intermolecular forces, therefore, so these 3 dots in a triangle formation just means therefore, lower boiling point. Meanwhile, let's go to the other end that we have here. So this compound, which is butane, that has more intermolecular forces, therefore, it has a higher boiling point. So BP just means boiling point. Okay. And we can also assume, like, since all of these, this is what you'd call it an analogous series, because like all of them have carbon and hydrogens in them, and like going from this compound to this compound, the amount of carbons increases by 1, and this is kind of getting into something that's explained in more depth in Chem 30, so I won't talk too much about it. But essentially, as we are reading from left to right, the compounds are increasing in size. Okay, so we can assume that in an analogous series, the bigger the compound, the more protons and electrons it has. Therefore, it has more London dispersion forces, and the bigger the London dispersion force is, the higher the boiling point. Okay, so if the molecules are all the same size, so that means, same number of protons and electrons, which the fancy word for that is isoelectronic, then we need to look at how many different intermolecular forces something has. Now, if it has all 3 types, so that's London dispersion forces, dipole-dipole, hydrogen bonding, then it would have a higher boiling point than a compound with just 1 or 2. Okay, so what that's saying is a compound with all 3 types of intermolecular forces is going to have a higher boiling point than a compound that just has 1 of the intermolecular forces, so let's say London dispersion forces, or just 2 of them, like London dispersion and dipole-dipole. So for example, we're comparing krypton versus hydrogen bromide, which would have the higher boiling point. Okay, so let's do our little analysis here. So we have krypton and we have hydrogen bromide. Okay. So, London dispersion forces. Let's create a little chart here. Okay. So, if I look at my periodic table here, so krypton has 36 protons. So let's write that out. Now, hydrogen, we know that has 1 proton, but how many does bromine have? Bromine has 35. Okay, so 1 plus 35 is going to give us 36 protons. Okay, so these are what you would call isoelectronic. They have the same amount of protons and electrons. So that doesn't really help us figure out which has the higher boiling point, so let's move on to the other forces. So we got dipole-dipole and hydrogen bonding. Oop. Okay, so for dipole-dipole, krypton isn't going to have it because it's just an atom, so there can't be a more positive side to it and a more negative side to it. So it doesn't have it. But hydrogen bromide, right? Hydrogen has an electronegativity of 2.2. Bromine has electronegativity of 3. So this is going to be polar. So because of the electronegativity difference, so it is going to have dipole-dipole forces. So I'm going to go, yep, it has that. For hydrogen bonding, since krypton is not polar, it can't be doing hydrogen bonding. Also, it doesn't have hydrogen in it, so it can't hydrogen bond. Meanwhile, if we look at hydrogen bromide, hydrogen is not directly connected to nitrogen, oxygen, or fluorine. So hydrogen bromide also can't do hydrogen bonding. So looking at all of the intermolecular forces here, both of them have the same amount of London dispersion forces. However, hydrogen bromide has more types of intermolecular forces because it has London dispersion as well as dipole-dipole. Therefore, hydrogen bromide is going to be the one that has a higher boiling point because it has more intermolecular forces. So hydrogen bromide has the higher boiling point because it has more intermolecular forces, which I'm going to abbreviate as IMF, intermolecular forces. Okay, so very important that the more types of intermolecular forces a compound has, the higher its boiling point will be. All right, moving on to the spectrum of change in bonding. So although we treat ionic and covalent bonds, which are the two main intramolecular bonds, even though we treat them as completely different, it's actually not so clear-cut in reality. There's actually there's a spectrum between ionic and covalent bonding. Okay, so if we're talking about nonpolar compounds, so an example of that would be something that's diatomic or something that has two of the same elements or atoms of the same element in it. Since they have the same electronegativity, which is 2.2, right? Both of these atoms are pulling on the electrons within this bond with the same force, but just in opposite directions. Okay, so nonpolar compounds, the electrons are going to be shared equally between the atoms. Meanwhile, with polar compounds, So let's say if we had hydrogen chloride. Okay, so if we look at chlorine, that's electronegativity of 3.2. Hydrogen is 2.2. So since chlorine is the more electronegative one, that means the electrons within this bond are going to be slightly more skewed towards the side with chlorine. And because of that, the electrons are shared unequally between the atoms. And with ionic compounds, so let's say we have sodium chloride. So sodium chloride gets formed when sodium, which likes to have a +1 charge to it, okay, and then chlorine likes to have a negative charge to it. So that means that sodium gives up 1 electron to chlorine. That's what causes sodium to become positive. Okay, because it's giving up its electron, it's giving up something that has a negative charge to it, and then chlorine has a 1- charge. Okay, and I guess you could even just do it like so. And if I'm drawing this Lewis dot diagram of an ion correctly, because the chlorine gained an electron to its outermost shell, I would draw all of the electron dots like that. Okay, but talking about the Lewis dot diagrams of ions, that isn't, don't worry too much about that. Okay, that's just me being extra. So in ionic compounds, the electrons are going to be transferred completely from the metal to the nonmetal. So sometimes the division between the 3 different types of compounds will have some gray areas. So although we generalize them into these categories, in practice, the compounds may have properties of more than one type of intramolecular bond. Last but not least, let's talk about solubility. So solubility operates off of this principle when we're talking about polar and nonpolar compounds. It operates off this principle of like dissolves like. So what does that mean? So it'll mean polar things dissolve polar compounds. Nonpolar compounds will dissolve nonpolar compounds. Okay? And then compounds with hydrogen bonding will dissolve other compounds that have hydrogen bonding. Okay? So again, it just comes back to like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Hydrogen bonding will dissolve other compounds with hydrogen bonding. Okay, with ionic, that is a topic that we'll get into in future units. Okay, but mostly for these comments here, that has to do with polar and nonpolar compounds. Okay. So if we're looking at some of these examples here, which of these would be dissolved in water? So first of all, let's figure out, okay, water, is it polar or nonpolar? So we can apply this rule of like dissolves like. So water, if I draw a quick picture of it here, okay, and then draw the little dipole moments. Because oxygen is more electronegative than hydrogen, that's why the arrows are pointing up towards oxygen. Okay, and the resultant vector of these dipole moments, so the small arrows beside the bonds, will be going up towards the side of the compound that has oxygen in it. Okay, another way you can figure out that water is polar is because it's an asymmetrical compound. Okay, so water, it's polar. All right, so let's look at our options and see, okay, what's polar, what's nonpolar. So looking at all of these compounds here, looks like they're all carbon-based. So the rule with carbon-based compounds that we've talked about in an earlier lesson is carbon with only one other thing is going to be nonpolar, but carbon with two or more other things are going to be polar. So let's apply that rule. So carbon is with chlorine. So carbon is with only one other thing. That means this is going to be nonpolar. And you know what? I'm going to abbreviate nonpolar to NP just to save on space. Okay. So carbon tetrachloride, that would not dissolve in water because water is polar and carbon tetrachloride is nonpolar. With methane, because it's carbon with only one other thing, this is also nonpolar. Now, we have CH3Cl, so it's carbon with two other things. That means this is polar. So I'm going to circle the ones that would dissolve in water. So CH3Cl, yes, that would dissolve in water because it is polar. Okay. Now, C25H52, so that's quite a large molecule there, but it's still just carbon with one other thing. That means it's nonpolar, so it won't dissolve in water. Now, CH3OH, so that's going to be methanol. So it's carbon with two other elements, which means it's going to be polar. So this will dissolve in water. And then last but not least, C6H12, that is carbon with only one other thing, so that means it's going to be nonpolar. So it won't dissolve in water. Now, out of the two of these here, both of them are polar. However, I can tell you that it's just methanol, so CH3OH, that is going to dissolve extremely well in water. Now, the reason being is because methanol can do hydrogen bonding. So if I were to draw a picture of methanol here, we can see that hydrogen is directly bonded to oxygen. And since hydrogen is also directly bonded to oxygen in water, both of these compounds can do hydrogen bonding. Therefore, hydrogen bonding can happen between these two compounds here. Okay, so what I'm trying to say is both of these will dissolve in water. However, methanol will dissolve even better in water out of the two of them. And the reason being is because it can do hydrogen bonding. Okay. Now, the second question saying, okay, which of these following substances would dissolve in hexane? So hexane, it's carbon with only one other thing. That means this is going to be nonpolar. So we're looking for other things that are nonpolar that will dissolve in hexane. Okay, so looks like we have all the same substances with the exception being water over here, but water we know that is polar. Okay, we know methanol is polar, this is nonpolar, this is polar, nonpolar, nonpolar. Okay, so the substances that are going to dissolve in hexane, since hexane is nonpolar, the substances that dissolve in it will be nonpolar as well. Why? Because like dissolves like. So these substances are the ones that will dissolve in hexane.